Okay. Okay, so let's get started. We'll talk a little later that talk today. But okay, let's start off. First of all, are there any just from announcements from last time and stuff like that? Again, just to make sure everybody picked up a copy. I'll send a couple extra copies of this going around. A couple of classes ago, I passed out the 100 problem read assignment. So if for some reason you haven't picked it up, just pass it around. Get it back there. Make sure everybody sees it. If you haven't picked that up yet, be sure to do so. Did anybody start looking at that or anything like that? You did. What was your reaction? This is going to be impossible. This is not
I don't know. I mean, how do you grade it? For example, how is it? The solution is good or bad? I don't know.
Okay, so the solution is the solution good or bad? You're saying, how do I grade it?
Yeah.
Okay. I think what I'm going to grade it on is sincerity. Okay. So I'm not really so. It is something that it is not. There's not necessarily a right answer or a wrong answer here, but I'm going to take a look and see if I think this was done in a reasonable way. Okay. So this is not meant to scare you. This is meant to say that assuming you guys do it in an honest way, I'm sure everything will be fine.
Also, just look at the question, but I don't know is it work or not. I don't know this method is work. I think it's work.
Oh, okay. So what you're saying here, there are a couple things. So what am I going to be grading on? I'm going to look at your answers. I'm going to click on the ones you like and see if these are reasonable ones to like. Okay? That's one way of doing it. Now, people have different tastes, so I can understand that but I would like to think that there's going to be a correlation between the problems you like and the problems I like. Okay, so I should be able to tell that your problems are more interesting than random problems. Okay, I know what random problems look like there. I should be able to see when I look at your thing, if I see 100 statements, each of which is the exact same thing, I know you probably didn't work on that very sincerely, right? There should be a mix of topics. There should be a mix of different things. Okay? So I'm not looking to get people in trouble. I'm looking for people to make a sincere try at it. Okay? And like I say, you may not know that your solution works in 5 minutes, and the answer is you're certainly right. Okay? I'm still looking at just sort of what would be your first attempt. Somehow when I read these things, I put them into a pigeonhole. Okay? And I say, okay, backtracking. Now, it may not be that, maybe in fact, if you look at it closer, you'll find that there isn't time for backtracking, or there's a better way to do it. So I'm going to ask you to sort of give me your impressions about the problem, okay? And I'm not going to punish you if your impressions are wrong, so long as your impressions are reasonable. Does that sound fair? At what speed were you going through them, if I may ask? Did you actually start trying to put down some entries?
Yeah. I just look at the question, but I think my solution is very. It's not very good because maybe time time exists.
What?
Because I just think a solution there is n square, O(n) square, but I think it's too slow.
Okay, so I don't. You're welcome to spend time to think about this and to try to come up with the right solution. And if you have anything interesting you want to tell me, again, there's that last field in the thing where you're allowed to tell me anything that you find that's interesting, right? So in fact, if you really get proud of something you want to do, you want to put a description there, I'd be happy to get it. But that's a little bit beyond the scope of what is needed. Okay? What is needed is that you make a good try at it. You make a try to classify the problem. If you get interested enough, you want to really think about it. Or you get interested enough that you even want to raise it as a question in here. Saying, hey, I was curious about this problem. Could we maybe talk about that? That might be a fun thing. I see people sometimes bored with some of the stuff that I'm saying. If you have a problem that you think is interesting and you'd like to raise it for everybody to look at, that might be a perfectly fun thing to do. Okay, so I'd be happy to have those kind of questions at the beginning. Okay? But in terms of time that I require, about 5 minutes per problem. That's really what I want you to spend. You're welcome to spend more, but that's up to you. Okay? Any questions? You can get more of these, yes. Anyone wants this, that's fine. Any other questions about the problem, read. Okay. So let's now go through the problems that we're studying. We've been talking about number theory. How many people got all 4 of the number theory problems? Okay, nobody. How many people got 3 of the number theory problems? I've got 2 people got 3s. Okay? Let's try again, because sometimes the same. How many people got 4? Okay, let's get all bodies in here. Okay. So how many people got 4 of the number theory problems? All 4 of them to pass. 1. Okay. How many people got 3 of the number theory problems done? Okay. 2. How many people got 2 of the number theory problems done? Nobody. How many people got 1 of the number theory problems done? 1, 2. How many people got none of them? Of the people who got none of them, how many of them tried?
I've tried 1.
You've tried 1, you've tried a couple. Okay. It's good to try it. So these problems seem to be scoring us harder than the other ones. Okay? So that's interesting to know about. Let's look at the problems and see what's going on. Now, the first problem is the Carmichael numbers problem. Actually, no, I guess we can view it from here. People like looking at it that way. Okay, so what is the, who wants to tell me what the Carmichael numbers problem is? Somebody who's tried it. Okay? Yes, you.
I've tried, but I have presentation error. I don't know.
Okay, presentation error.
Yeah, I still got presentation error, but UVA can pass it.
Okay, so the first question is, I noticed when I signed on here that nobody had successfully gotten this past the judge. Is that right?
Yes.
But you got it past the UVA judge. Is that right? Okay, so one hint might be, go to the UVA judge. But because that evidence looks pretty damning that there's something wrong with the judge here. But let's go and take a look at that. So what is the problem? Tell me what your problem is. What the problem is.
The problem is that there is a test to, as it is very difficult to find a prime to test whether a number is a prime. So there is a mathematical method to test it, which is something.
Randomized primality testing, right?
Yeah.
Okay. Does everybody understand the idea? So there's this congruence that's basically holding. Okay, that says that that if n is a prime number, then for all integers a raised to the n mod n is congruent to a. Okay. Whereas for most integers, a raised to the n mod n is a number between 1 and a. Okay? 1 and n, or 0 and n minus 1. What is the probability, if we just thought these were random things, what is the probability that a to the n mod n should be a? Okay? At least a heuristic probability, not a well-defined probability. But what would be the likelihood if I gave you an arbitrary recurrent congruence like this? That in fact, a to the n mod n is going to be equal to this. Okay. What? 1 over n. Does everybody see that? It's unusual. The way I think of it is being a to the n is a big number. And the mod n is having it go around a roulette wheel, okay, of n slots. And the remainder is which hole it will fall in if you have a roulette wheel. Does everybody see that? You go to like the Macau. You know about roulette? There's these roulette wheels, right? And there's balls that fall into a slot. Here we have a roulette wheel with n slots, right? We roll the ball around many, many times, right? People can still bet actually at this point, if I'm correct, right? But then eventually it starts running out of gas, ka-chunk, 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 and falls into a spot, right? A to the n is in some sense the long path. N is the width of the roulette wheel. A is the slot it falls in. If you throw it, do the roulette wheel n times, a bunch of times, and it always falls in A, you know that the roulette wheel is cheating, right? And that's sort of the idea of this prime test. Okay? It seems very unusual that, that it was a 1 in chance it should fall into this slot modulo any number theoretic considerations. Okay? The interesting thing is there's certain numbers for which this fails, and these are called the Carmichael numbers, right? So your goal is to find all the Carmichael number, or a Carmichael number. Test if a number is a Carmichael number, correct? How do we do it? Okay? Someone who's done it. Okay? Well, actually, someone who hasn't done it. Someone who's tried it. How have you tried it? You think yours works, but you think that the UVA judge is just not taking it, right?
Oh no, I used the programming challenge, and there's
right. Programming challenge isn't accepting it, but presumably it will. Part of the problem is likely to be that the UVA judge seems to be better for this one. Okay, so try it there. How do we solve it? How do you solve it?
Actually, I use a brute force algorithm.
What does brute force mean?
I first construct a prime table between 1 to 65,000.
So you construct a table of all primes up from 1 up to 64,000. Does everybody agree with that? Okay. How long does that take? Does that take an interesting amount of time or not an interesting amount of time? Probably not an interesting amount of time would be my guess, right? Does anybody know how long it takes their program to do it? What?
Very fast.
Real fast.
Very fast. Very fast to calculate all the prime number between 2 and.
It's very fast. Okay, so yes, so we can do that by, if you think about it, at 65,000, the number of divisions you're going to be trying is the square root of 65,000. Right? What's the square root of 65,000? Is that a lot or a little? I'm trying to think this thing through. What is the square root of 60,000 about? I guess it was the square root of 64,000. Would that be easy? That would be 8 times the square root of 1,000. What's the square root of 1,000? 30-ish. So that means you're doing about 240 tests, potentially, for each integer. Okay? And usually a lot less. And in fact, you're not going to do it for odd numbers, or you're going to fail the odd even numbers very quickly. Right? So I agree that primality testing should be quick. What's the next step?
And then I just build a function to test if it is if the number can pass the Fermat test.
Okay, so the basically thing, how do you now test if it passes the Fermat test?
Brute force, actually.
Brute force. Well, what does brute force? There's different degrees of brute force. What does brute force mean? You have 4 I goes from 1, A goes from 1 to N, probably, right?
I see. I use recursion to every time the recursion reduce the problem to half.
I see. So what you're telling me is that you're computing that in order to compute what this is, you're not going to be computing this looping through n times. Is that right? You're using a recurrence to compute this thing in a logarithmic number of multiplications. Is that what you did?
Yes.
Does everybody see that's the first step that he did? Okay? He's claiming that in order to compute a to the n, you only need to use a logarithmic number of multiplications. I think we showed that in the arithmetic section. Is that right? Does everybody know how to do that? Or who doesn't know what I'm talking about? Raise your hand if you don't know what I'm talking about. Okay, raise your hand if you do know what I'm talking about. Okay, good. Okay, so we agreed that we could do that, but the other question is, did you do this for the whole multiplication all the way out? Did you do this as modular arithmetic, or did you do this as explicit arithmetic?
Sorry, I can't get the point.
Okay, when you compute the exponent here, did you compute a to the n fully with long integers? Or how did you actually compute a to the n mod n?
Oh, I first calculate a square mod n and then let the n over 2 and then...
So right, so the basic principle here seems to be that somehow that a to the 2k mod n is going to be equal to a to the k mod n squared mod n. Everybody see that? And because of the miracles of modular arithmetic, we can compute this thing in a logarithmic number of multiplications, and the multiplications never get bigger than n. Does everybody see that? Okay? Any complications here that people see? Okay? Did anybody have any troubles getting this accepted once you found the right judge? Okay? Any complications with this? How many Carmichael numbers are there, by the way, less than 65,000? Are there a lot or a few?
Few.
How few? What?
Less than 10.
Less than 10. Okay, if there were a lot, this is a pretty lousy primality test, right? Suppose we do the Skiena primality test, which says that any prime times 0 is equal to 0. Then that would work for all composites too, right? So the only reason that this would be a good primality test is if there's a small number of counterexamples. And even better would be if if there were a finite number of counterexamples. I don't think that's the case. Does anybody actually know? I don't believe that there are a finite number of Carmichael numbers. Okay? I think it may be that there's an infinite number. Okay, but there's a small number. How would you find out if there was an infinite number of them? Just from what we've talked about here. What would be the way that you would find that out? Okay? I know how I would do it. I would take the 10 numbers that you found, and I'd type it into Sloan's Handbook of Integer Sequences, right? And see what numbers came up there and what the literature there was. That would be my personal way of doing it. Okay? Any questions? Okay? Would your program, now this program problem is a little too easy because it's limiting things to 65,000. Did anybody try to run it for a larger value, just out of curiosity? How big did you run it for?
I don't know, but I think we don't need to look a from 1 to n because we need to only run all the prime number below the n for the a. I mean the a is only the prime number we need to test.
Oh, okay, interesting. So you're now proposing a faster test, which if it's true, that would be interesting. Let's think whether this is true or not. You're saying, I don't need to try all A's. I only need to try prime A's. Does everybody see that? I don't know if that's true or not. If it was true, that would be a good thing, right? Instead of doing n of these, you would do n over log n. Okay? Since you have the prime numbers, that would be good. Can we prove that?
Because it can factorize. Assume that the prime numbers more than a has this equation is right. So we can factorize a into 2 or more prime number, and then if that two answer times together and the mod n is equal to itself, so it's right. Yeah.
Well, I don't believe this right now. Wait, so you're telling me that if you, okay, so you want to tell me is suppose P1 times P2 is the prime factorization of n. Okay, let's say n is equal to this. Your claim would be that
no, I mean a equal to this. A equal to
that a is equal to P1 P2. And your claim is that that this congruence will hold if it holds for P1 and P2. Why is that? Okay, that's an interesting speed up if that's true. Although, is it a speed up? Let's first think about it. There's two questions. First, is it true? And second, is it a speed up? Okay? Okay? Why do you say it won't be faster?
But you have to test all.
Okay, if the theorem is true, then presumably you're testing it for all prime factors, all primes. Okay, he's already calculated the primes, so there are less primes. He's only going to, if this was true, he's only going to do it Oh no, but then for any A, what he's got to do is to have the prime factorization of A.
What? Do you factorization A or factorization?
Factorization of A. So we only calculate the prime number for A to test it. We don't need to find the composite number of A to test it. We only test the prime number A.
Well, what I think is that if you got prime, say P plus this, and in fact N is fixed, and if you got another prime Q plus this, and I can confirm that PQ plus this, and I don't have to test. That means that you only test those smaller than N primes.
Yeah.
Right.
And you don't have to factorize primes.
No. I mean, just calculate the prime number of A.
So you factorize.
Yeah.
Factorize.
What you're claiming is that if in fact, maybe I don't know if I believe this, if A is composite.
Yeah. If A is composite, it's true always.
No, I think if A is composite, you think if A is composite, this is always true.
Yeah.
This recurrence is always true for any composite?
If A is composite and all the case below lower than A is true, then A is true. If A is a composite number.
It's the same thing. It's the same thing that you just test those primes. And if you
Wait, no. But for all primes. Oh wait, no. I guess okay. I see. You're saying because N is not the prime. Okay. You're saying that if A is a prime to the N mod N is congruent to that prime.
But as far as I know, all primes can pass this test. Otherwise, this test is useless.
Right. Okay. But no. But the trouble is that the prime is an N. He's making a claim about a prime that the primes of what happens if A is prime.
Yeah.
Right.
We only need to test if A is prime. Yeah. We don't need to test A from 2 to N.
Okay, so let's think of what that would mean. If it was true that you only had to test it for primes,
I see.
then in fact it would be potentially a little bit faster. Okay, because he already has the list of primes. Okay, and you would only have to look at N log N thing. The trouble is he's really trying to test whether N is prime. And in principle, trying to test if N is prime can't be that much harder than testing if N minus 1 is prime. Right? So in general, for the Fermat test, it's hard to tell which are the primes. Right? For our example, because N is so small, it's easy. So if what you're saying is true, I don't think in the long run it helps to speed it up. Because implicit to take advantage of what you're doing, you need to know that N minus 1 is prime. Whether N minus 1 is prime. And if you need to know whether N minus 1 is prime to test if N is prime, then that doesn't seem like much of a win. Does that make sense? Okay, but anyway, interesting. Okay? Any other questions or comments about this one? How many lines long were your solutions? Let's just take a look at this question. How long was your solution?
Of like 100.
100 lines. How long was somebody else's solution?
50.
What?
55.
55. Okay. Did you do anything to make it short? That's interesting. Did you implement your fancy test here that you were describing?
When I'm doing, I just do a proof, but I forget how to prove it. Use my method. I use my method to test the prime first. Yeah. But I don't know.
Okay, so you're adding extra code to implement these things faster. Okay, I would say it was not necessary in this problem. Although I give you points if you actually proved it. That's actually interesting. Okay? Any questions? I'm not. What you're saying is plausible, although I have to see a proof before I really will say that I believe it. But it's plausible. Okay? Anybody else? How long were their programs? Okay? 55 lines. And anybody do anything shorter? How long was yours?
34.
34 lines. How did yours? Why was yours so short?
Because I calculate the prime, all the primes in that range, 65,000 in a very short. I calculate all the primes in 5 lines.
Okay, you build the array of primes, you mean, in
Yes.
5 lines.
So-
Okay.
So in terms of calculating all the primes in this part, my program is very short.
Okay. Interesting. Actually, you know what I wonder about? I wonder if you could calculate the primes even shorter, given that you have the Carmichael number test. Certainly any prime would satisfy this test, right? There's no reason why you had to actually do the prime test first, right? You could calculate for all numbers from 1 to n whether they pass the Fermat test, right? And then the question is it easy to now separate out which of these is prime? Okay? I guess by definition, a number would be prime if it's not divided by any smaller Carmichael number. That would actually be a sufficient way to do this one, right? Because if this test holds for all primes, if you did the Carmichael test, okay, you could build up an array of all things that pass this test. Then by definition, to test if a number is prime, all you need to do is to compare it against all the Carmichael numbers. And if none of them divide equally, then the number is prime. Okay? That might be a little bit easier. Although this is not a hard problem to begin with. Any questions? How many people think that's a reasonable way to do it? How many people don't think it's a reasonable way to do it? How many people didn't understand what I was saying? Okay. Yeah.
Just want to prove.
Okay, you want to give us your proof. You want to put your proof on the board? Fine. That's good to know. Go.
So, A equals to P1 times P2. No, A.
A is equal to that, right?
So, A n log n equals to P1 times P2 n log n
Right.
equals to P1 n log n P2 n log n equals to P1 P2 log n. And this one is equal to n log the a log n. So equals to n.
So we don't need to test this number for this.
Okay, so let's hit what we're saying here. So this, I think, this is this multiplication. The step from here to here, you're applying the result of the Fermat test, right? That the claim, the claim is that p to the n mod n is equal to p
Yeah.
if p is prime.
Yeah.
Is that right? Now, where did we prove that or claim that?
We just test the previous from the lower bound is from the minimum to maximum prime number, and then prove it by
Wait, no. What I'm just trying to figure out is here,
here.
there is a claim, okay, that for any n, whether it's composite or not, okay, p to the n mod n is congruent to p.
Yeah.
Is that right?
Right. But we did. In previous we found that P1 is true because P1 is smaller than A.
p1 is smaller than a, yeah.
So it's true if we count it by from the smallest prime number to the higher number. If P1 is a prime number.
Yes.
Yes, I think that's true. We can simply put P equals to xy plus y, where it's n plus y. Then we can find out the Pn mod n should be P to the n, the answer to P to the n. But P1 mod n should be only P. These two can be a different value.
Okay.
Let me write that. For example, the prime number is from 2 P1 P2
Right?
and then it's A, but A is not a prime number.
Right?
And then we prove this one, and then this one we assume is true
Yeah.
by induction. So this one will be true automatically.
The inductive assumption you're making is what?
If this one is this one can pass the test, this can pass the test, then this one no need to check because it's pass the test automatically, and because this one will.
Oh, okay. So you're making a claim now about that if, because this is smaller, it passed the test. This passed the test. You're saying it suffices now to compute. Oh, but by definition, this is equal to A mod A. You're right. Okay, I think I believe that now. Okay, interesting. Okay, any questions? Okay, fair enough. Anything else interesting about this particular problem? Okay? Anyone? Okay, fine. Let's go to the next problem. Which is the next one was factovisors. How many people got factovisors? Okay? Somebody who got it or tried it, tell me what the problem is. You. Let's try you for today. So what is the problem about?
It's about if you two number m and n,
Right?
and you have to test whether m divides the n factorial.
N divide
M
m. This
f divide
m divide n factorial. Okay? How do we do it? Okay, any questions about that? How big can m and n be? They can be up to 2 to the 32, 31. Okay? So it's too big to do this by explicitly computing 2 to the 31 factorial. Does everybody agree with that? Okay? I think that's pretty clear. Okay? How do we do it? Somebody, any ideas as to how we do it?
I factorize n.
You gave the prime factorization of n or m?
M.
M. You wrote n is equal to p1 up to pk, right?
I factor up to its square root.
Wait, factored it up to its square root.
Up to its square root.
Okay?
But just factorize it.
I'd say factorize it completely. Okay? Although if there's a reason why you can get away with less, we'll talk about it. I'd like to talk about it at the end. But what you then do?
And for each factor, say p,
Yeah?
I've got a counter, count how many p's there in n, and I calculate how many p's will appear in n factorial.
Okay, so the question is, in the factorization of this, we have the number 17, let's say. The question is, how many 17s are there in n factorial? How do we compute that? Okay, someone on that side of the room. How do we compute how many 17s there are? Times 17 is a divisor, okay, of n factorial. Or specifically, what's the largest value of q, such that 17 to the q divides n factorial? How would we figure that out?
Q times 17.
You would say that it is q times 17. What do you mean by that?
Is it tested? Is it bigger than?
I see. So what you're saying basically is that q, I think you want to say, is something like n over 17. Is that right? Because basically 1 out of every 17th numbers, we're going to go multiplying it. There'll be 17. When we multiply it by 34, there's a 17. Right? Is this a ceiling or a floor? Floor. I think that this is right. Okay? So in general, is the solution to this, for any particular prime, do this formula here, okay, and then see whether this value is larger than the exponent in the prime factorization. Okay? Is that right or wrong? Wrong. Why is that wrong? Okay?
Say it got 7 squared. Say if n is bigger than 7 squared, and you do that, you're missing at least one factor of 17.
What you're telling me is, suppose let's say n is, let's try it now with a simpler example. Suppose we consider the prime number 2. Okay? How many times is 2, for what power is 2 to the cube? A divisor of n factorial. Okay? It's not going to be n over 2 floor. Why not? How many 2's are there going to be in the expansion of n factorial? There is a 2, 1, 2, 3, 4, 5, 6, 7. Let's take 10 factorial. How many 2's are there in the product of this? There is 1 2 here, but there are 2 2's there. Does everybody see that? There is 1 2 here, 3 2's here, 2 2's here. So how do we get the right count? Okay, we need the right count of how many times each one of our primes is a fact divisor of it. Does everybody see that? How do we get a right count on that side of the room?
The summation of the fact is divisible by 2, and then the sum of the how many numbers can be divisible by 4 and then by 8.
I see. So you want to tell me that the right answer is that Q should be equal to the sum as I goes from, let's say, 1 to something. We'll have to figure out what that something is, right? Of the floor of n over 2 to the I. Does everybody see that? This is going to count how many 2's, first of all, are less than 4. How many even numbers are there? Multiples of 2. The second term is going to count the number of multiples of 4, because we're going to pick up an extra 2 for every multiple of 4. The third term, too, will count the number of multiples of multiples of 8. Does everybody agree with that? So this looks like the right answer to me. But what is the exponent that we need to use? How high should our sum go? It's not an exponent. How high should the limit of the sum be? Something like log base 2 of n. Does everybody agree with that? We might as well make it a ceiling just to be sloppy. But that's how many terms we would look at. Right? And if we do it this way, we can count how many times there are and do that division relatively straightforwardly. Any questions about that? I think that's now sort of clear. Okay? Any tricks about programming this one? Let's think about this. Okay? Is everybody, any questions about that solution? Okay? Any tricks about programming this one? Is it going to be hard to find the prime factorization of one of these numbers? The numbers are up to 2 to the 31. Is that going to be too big to find the prime factorization of? We have to test up to the square root of it. What's the square root of 2 to the 31? Two to the 15, what's that going to be? 2 to the 15 is what?
9,000, isn't it? Oh, sorry.
2 to the 15 is about 32,000, I think, or something like that. So it's not so frightening, okay, to do that kind of factorization. And then once you have it, then you're in business. Okay? Any questions here? Any subtleties on this that anyone can see? If you got it working, how many lines long was your solution?
I don't know.
How many ideas?
line.
21. Okay. How many lines long is yours? 40. 40. Okay. So, okay. Anything magical about how you got 21 lines?
It's easy to do the
Factorization.
And then I check, calculate Q, and then to see which, if there is one Q is bigger than the less than the exponent, I can immediately break out and return.
Not that.
Otherwise, at last I can print out the yes, okay.
Okay, fair enough. So it's basically this approach. But then nothing particularly clever you're thinking about. Okay? Any questions about it? Okay? Good. So I was like, now this one, people got through the judge, right? Okay, fine. We'll try to. Someone who failed on the Carmichael numbers problem, let me know, and we'll see if there's a problem with the judge on that. Okay. What's the next problem? The next problem I think is more interesting. It's the marbles problem. Who's tried the marbles problem? Okay? Tell me what the marbles problem is.
You have a certain amount of money, and you want to buy two types of marbles.
Right?
And
two types of boxes for marbles, right?
Yes. Your volume of your box is a certain number, and each marble is also.
Actually, what's interesting is I think the problem is asking for you're buying boxes, okay, that can hold exactly this many marbles. The truth is you could view it equivalently that your each box costs this much and gives you that many marbles. Okay, I think it's sort of an equivalent formulation. But what's the question now? So you've got two types of boxes, each of which have different capacity and each of which have different costs. What do you have? You now have a target integer that you want to realize?
Simply you have an equation to solve and to minimize the cost.
Well, what you're saying here is you now then are given that you have a certain number of marbles you want to have, which is in this case 43.
Yes.
And you want to figure out how to buy a set of boxes that add up to 43 capacity, whose cost is minimized. Is that right? Okay, so let's think about this problem. Suppose we didn't worry about costs. Now I will tell you that I've got a target integer here, n. I've got my box sizes. What are my variables? Okay. N1 and N2. How can I figure out if there is a way successfully to represent these marbles using that many boxes of that size? Okay? Let's just think about the existence problem first. Because over here it says here sometimes it fails. According to this, you could not make 40, if n was equal to 40, and these sizes were, I guess, from that smaller example, probably 9 and 12. The claim is that there is no way to do that. Is that right? Whereas with the other one, 43, and 1 and 2, if we have these things of size capacities 3 and 4, the claim is there is a way to do it. Okay? How do we compute whether there's a way to do it? Does anybody have any ideas? Just the existence problem. Okay?
Use the GCD.
You say use the GCD algorithm. What does the GCD algorithm have to do with it?
It's an equation, and you want to find there exists a solution
Well, so the GCD of which numbers? GCD is the greatest common divisor, or you want to run it on what? Which numbers?
N1 and N.
You say, let's compute that, let's say that G is equal to the GCD of N1 and N2. Okay? What's going to happen now that we have it? Okay, now that we have that, what do we get?
And N can be defined by G.
What?
The big N can be divided by G.
Okay, and you're saying that if N is divided, if G divides N, then you claim that gives a solution. Is that right? Or not?
And you have to try. There is some more possibilities because the solution must be non-negative.
Okay, so we're hearing something complicated. Is there a simple way to tell whether or not this is true? Okay, let's first try as an elementary thing. Is there an elementary way to tell if 40 can be expressed? What do we really want to do here? I claim that this is something that is there a way to write this as a Diophantine equation? What is a Diophantine equation? I didn't say that last time. But it's an equation that is defined on integers. Okay? So, the most famous Diophantine equation is this one, is a to the n plus b to the n equals c to the n. For integers n, if this is an equation which has 4 variables, a Diophantine equation is an equation where we restrict it to integers. Okay, how many people here have heard of Fermat's last theorem? Who here has never heard of Fermat's last theorem? No one's ever heard of it. Oh, that's interesting. Okay, this is good to know then. There was a very famous problem. This guy Fermat, the same Fermat of Fermat's test, he lived about 300 years ago, was a lawyer and a number theorist. Okay, when he wasn't doing law, he did number theories. And he was interested in, are there values of a to the integers a, b, c, and n that satisfy this equation? Does anybody know of any a, b, c, and n that satisfy this equation? What? For n equals to 2, that's actually well known. Then you get a squared plus b squared equals c squared, right? Are there any integer solutions to this? 3, 4, 5. These were, I think, what are these called? I think Pythagorean triples or something like that. Right? Because this is like the Pythagorean theorem, right? This said that an integer edge triangle, you could have a triangle here of edge 3 by 4, hypotenuse 5. Right? Okay? And that would be true. Okay. Fermat, though, couldn't find any triples for n equals 3 or any larger exponent. And he figured out that, that there was, in fact, he could prove that for all n greater than 3, this thing did not have any solution in the integers. And he wrote in his little book, he had his math book he was working on, and he says, I have a proof that this can't be, that there exist no solutions for n greater than 3. But it's too big to put in the margin of the book. Well, people spent the next 300 years trying to find that proof, and nobody found it until about 10 years ago. There was a guy named Andrew Wiles who proved that there is in fact no solution to this. Okay? And so what's the lesson? If you want to try to fake your way through an exam, say I have the answer but there isn't room to write it. Okay? The other lesson is that equations, when you restrict them to integers, are often very hard to solve. Does everybody see that idea? That's the other, is maybe the more important lesson. We're used to solving equations by algebra. When they're restricted to integers, they become Diophantine equations, and they're often very hard to solve. Any questions? So what is the Diophantine equation we want to solve here? Okay? Suppose I want to know, to solve this thing, what is the Diophantine equation for this kind of an example? Okay? Can anybody write down the question of, is there a solution to give me an equation? And does this equation have any solutions? What would the equation be?
N1 times x
Times x
plus N2 times y is equal to N.
Okay.
And minimize.
Okay, then there's a question of cost, right? Okay. But let's take a look at this thing. So now we wrote this one. This is really saying, is 40 equal to, does there exist a formula, n 9x plus 12y equal to 40? Okay? Any questions about that? So how could we solve this kind of an equation? Okay. What? So the first question, let's look at first, is there a naive way to do it? Okay, before we get into what I'll call the number theory high-powered way to do it. As a programming contest person, is there any way to do this? Okay, that would be interesting. Okay, let's say you don't know much number theory, but you want to look for a solution like this.
Try all the possible value of y.
Try all possible values of y. Does everybody see that? Okay, that we could prove it conceivably in this case by trying y could be equal to 0.
1 through 3.
And once we have it equal to this, then there is a, basically, I guess it's a question really of if you try it for a given value of y, you're saying x equals 40 minus 12y divided by 9. If this is an integer, you have a solution. If not, you don't. What's the largest value of y you need to try? Okay? The largest value of interest is pretty much going to be the ratio of this and this, I think. Right? The claim would be what? What would be the largest value of y? I think the largest value of y you would be trying would be 40 over, the ceiling of 40 over 12. Does everybody agree with that? Is this a big number or a small number of things to try? In the context of this problem, is there a lot of things to try or not? Okay? How many things might we have to try? Oh, this is not in the problem now, but let's go back to this. In the context of this problem, might there be a large number of things to try? A prohibitively large number of things to try or not? Well, let's think about that. Is it true? N would be how big? 2 billion. What? Well, if it's equal to 1, then there might be a special case. But you're right. At the very least, let's say the simplest case that probably is hard to think about is maybe 2. Okay? 1 or 2. That means you would have to do 2 billion tests here. Okay? So that is potentially problematic. Does everybody agree with that? Is it impossible, though? It's not clear it's impossible. Okay?
Suppose you got 2 billion, n equals 2 billion.
Yeah.
And n1 equals 1 and 4 nines following. And n2 just makes the total sum to be 2 billion plus 1, like 2. And you have to manipulate no more and equals so until last time.
Okay. Wait, so what are you saying here? You're saying basically, I think there might be 2 billion numbers you need to test. Is that basically what you're saying?
Well, if you pick the bigger N1 and 2, then pick the bigger one from those.
I see. So you're telling me that if I want to try all solutions, I could also just as easily use the bigger one, okay, as my boundedness test, right?
Yeah.
That if let's say I had 12 and 900, it would be fewer iterations if I started with 900, and I agree with that, okay? So we could, in principle, do this by brute force enumeration, but it's potentially expensive, yes?
Well, if you always, well, maybe, never mind. I was going to say if you always started with one that costs more, then maybe you could also get the cost out of the way at the same time, but maybe that's not true.
Well, the way that okay, so the good thing about the brute force might be it might solve the cost thing. What do we know? If there's a bunch of different solutions, we want the cheapest one, right? Which is going to be the cheapest one? Okay? How can we describe of all solutions which is the cheapest one? Okay? Is there any interesting property of that? Okay?
Well, I was going to say you just pick the most costly box and start from the one with that and go up until you find an answer, that would be the cheapest, but that's not true because the other one might hold a lot more marbles.
So what the argument would be is you're buying two kinds of boxes. There might be many different solutions to this equation, right? You want the one of cheapest cost. Okay? The one of cheapest cost is going to minimize the number of expensive boxes you use. But it's not exactly the expensiveness. What would be the right way to figure out which one you want to minimize? Cost to capacity, the price per pound. That's what I would be thinking about, right? That if, let's say, using these boxes, I can pay $1 per $1.2 per ball, per marble. And the other one cost me $3.2 per marble, right? To minimize the cost, if I have to store all the marbles, I want to use as many of these or as few of those. Does everybody agree with that? So I do think that the brute force, one good thing about the brute force is it would give you the cost right. Because you want the one that minimizes the use of the expensive boxes. Okay? And the only trouble seems to be that you're going through too many of them. Any questions? Did anybody try the naive solution like this and see if it timed out? What? Time limit exceeded. Okay, so that means we need to be smarter. Okay? Any questions? So now tell me about the GCD. Okay? What is the GCD? How do we use the GCD for something like this?
First, you solve the.
Oh, before I go through that, let me tell you what I think the answer is going to be. Here, I have, I'm saying that there is, if you look at what I'm saying here on the board, the most important class are linear Diophantine equations, which are of the form, okay, AX plus minus NB, where X and Y are the integer variables, and A, B, and N are integer constants. Okay? Does everybody see that? That looks like my equation here. Does everybody see that? So what I would like to say is, it looks to me like this kind of an equation, okay, is interesting because it is of the form of a linear Diophantine equation. And linear Diophantine equations can be solved reasonably. Okay? Not like Fermat's theorem, because that nobody knew how to solve, right? But linear Diophantine equations aren't so bad. So the claim is that if you have a formula of the form AX minus NY congruent to B equal to B, the solutions there, okay, are given by all X, where AX is congruent to B mod N. Why is this formula equal to this? Okay? People see what I'm saying now? Okay? We're saying that if this is equal to this, then we could rearrange it and say that put nx, ny over here, b over there. You've got a formula of the form ax minus b equals ny. Ax minus b mod n. Okay? This is going to give us, let's think about this. The claim is, what does this say here? If we have any integer a, if we have any integer x that solves this equation, this congruence, then the claim is that there is going to be a y that will work for it. Okay? That, I think, is what the claim here is. Right? And so this reduces to solving that congruence, which is a linear congruence, which we talk about how to do over here. Okay? So that's one way to do it. But that doesn't have anything to do with GCDs. How would you have solved this problem? Yes, come. Go.
I first solved this. And if the big N then there is no solution.
Okay, well, let's think whether this is true. Okay? So the claim here is you're going to be solving equal to ny. Okay. The first claim is, suppose, let's say, we have the answer to this. Right? Which presumably we get by using the GCD algorithm, right?
Yes, using the extended GCD.
By extended GCD, the thing that produced those extra integers that added up the things, right?
Yes.
Okay?
And then
So if this is true, okay, so what do I believe? I believe that you can get the solution to this equation using the extended GCD algorithm.
yes.
Do people see what he means by that? Do you know what I mean by extended GCD? Remember how we talked about how there were other integers that were picked up in the course of this, right? Extended GCD, we're generating these x and y, and that's what he needs there. Okay? Now your claim is the second claim, right? Why, if this does not divide that, is there no solution?
Then I get a group of get one solution. Yes, maybe x so and y open. And
Wait, no, the first thing that I see here, which I don't know if everybody, well, I assume everybody, but if I think about it, certainly if this does divide it, okay, then there is a solution. Okay? Why is that? Does everybody see that much? Because the point is that there is a set of boxes that will multiply to reach this. We know that n is equal to, we said this thing is equal to the GCDG, some integer k times the GCD. If we multiply k by x1 and x2, that would give us a solution for n. Okay?
But xy may be negative.
What?
yes. Then
Okay.
so
So what if xy is, okay, interesting. So,
every group of solution can be represented by and you and there are and you have to satisfy and you solve these two integration and find whether there is a t can satisfy these two integration. If there isn't this one, there is no solution to.
Well, wait. Okay, so let's take a look at what he's saying here. He's saying x naught is equal to the x prime we get from before, right? Plus what is x naught and y naught here? What are x naught and y naught? Yes.
It means every solution to each to
I see. So you're listing all possible solutions you're claiming are of this form for some t.
yes.
Okay? Okay, why is that?
You just plug into this equation and these two things will cancel out and this can represent all the solution of this equation.
Okay? Interesting. Okay?
And you try to solve if there isn't this, there is no solution for t there, then the equation will have no solutions.
Okay. And so how are you solving for t then?
Just
I see. Oh wait. So you're plugging in this entire expression into here. This entire expression in, wait. So no, I'm not seeing it, I'm afraid. Maybe I'm being dumb. But now how do you go from this?
from this to what?
This to a procedure to solve it. Okay? I believe that this is the set of possible solutions.
Yes.
Now, how do you figure out which one to use? What t is it that you should use?
To minimize the cost.
Right.
Then x off and y off must be the one of them should be minimized.
We should minimize the one that has the most expensive price per marble.
Yes.
Right.
One of them should be minimized.
Subject to the constraint that it's greater than 0.
And you have these two things, and you choose either one side, and find a smaller one, and that is the answer.
Okay? Okay, I think I believe that. Now, okay? Any ideas here? Okay? So the interesting thing is that, again, we broke it down into a case where basically we come up with a formula to describe all possible solutions, okay, and then took the smallest values that satisfied that, okay? Any questions about that? Okay? Any questions? Okay. Let's go through the last problem now, because while we have a little bit of time. The last problem is also a very interesting one. Okay, the repackaging problem. Who's tried the repackaging problem? Okay, you. Tell me, what is the repackaging problem?
There are many packages, and each package is defined by 3 kinds of integers: S1, S2, S3. And for each kind of package, there are unlimited number of it, and we want to choose some of them to form a new package, and each the new package S1, S2, and S3, they must be equal, and you need to write a program to tell, is it possible to find such a solution?
Right. So with this particular example, telling you that there are boxes. You can buy a package that has 1 cup of type 1, 2 cups of type 2, 3 cups of type 3, 1 cup of type 1, 11 cups of type 2. There's 5 cups of type 3. There's 4 possibilities. The question is there a way to pick some multiple of each one of these number of packages? So you can buy a certain number of each package such that the total ends up to be a case where they are all even. Okay? What is the answer for this one? Is it obvious what the answer to this one is? It's only not immediately obvious to me. Okay? Does anybody see how to do that quickly? Yeah. The input, there is an example up here. Is this the input example that they had? Ah, okay. So the claim here is that's the immediately obvious way to do it. So the claim was that if you bought 3 of these, 1 of those, and 2 of those, it will add up to be all 16, 16, 16. Okay? Any questions? So how do we go about doing this? Okay? How do we find out? Any ideas as to finding out how let's say whether there was what the heck there was? Okay? Any questions? Any ideas? Yes.
Right down.
Okay? And again, I prefer naive ideas first, just to make sure everybody gets into it.
For example, if there's only 2 packets, A and B, not 3, for this packet, 1 is A larger than B, and 1 is C and D for D is larger than C, we can easily to say that, see that it can pack it into 1 E and how to say
That's something that would be AD.
Yeah.
The way to do it that AD plus.
Yeah, we can pack the 1 is EE. It's simply to prove that.
Right. So okay. So everybody see that if there were 2 dimensions instead of 3, the claim is so long as both, let's say 1 cup is overrepresented in each of the 2 packages, the claim is that there is a way to do it. What are these values of E, just to make sure everybody's with it? Okay? What value of E would it be? Okay? If we have a cup here where A is bigger than B, another one where D is bigger than C, how would we solve for what E is? Or any E that would work?
Equation.
Yes.
XA plus XC is equal to E.
What was it?
XA
XA plus
XC
XC plus YC
YC
is equal to,
equal to
actually really I guess it's going to be what? XB plus YC,
yes.
YD. Does everybody agree with that? How do you solve for Y and D, X and Y? Is there a way to do that?
We don't need to solve this equation.
We don't need to solve it because they just say yes or no at the end,
Yes.
right? That I believe. But how do we know that this is, whether this is solvable or not? Okay?
If there is one constraint, that is X and Y must be larger than 0.
Okay?
It must be possible.
x and y are greater than 0. That's certainly true. How do we know that this is solvable, though, for the two-dimensional case?
Three-dimensional case?
No, for the two-dimensional case. You're claiming that this is always solvable.
Yeah.
How do we know that? Presumably you need to give a multiple that would realize it.
Yeah, the multiple, but I forget the equation.
Let's see if we can work that out, but that shouldn't be too hard, should it? What is an amount that an x and y that would satisfy this property? Okay? What if we did,
It's very easy to solve.
what is it?
Because there is this this is positive.
But both positive. Both positive, right?
These two numbers are positive, and then we can, for example, this is A, this is B. Suppose
Right.
this is B, and there is one possible solution that is suppose
BA, right? Yes. Everybody see that? That's exactly the right way to see it. Okay? So it should be clear that for two, this is like normalizing a fraction, right? Finding the common denominator, right? So basically, that we agree with. So for any pair, for 2 dimensions, this is now easy. Does everybody see that? What about 3 dimensions?
So I let this one be A1, A2, and A3. First of all, we make a table to see that is there any. The first one is larger than the second one, and the second one is larger than the first one. So A1 is true or A2. If both of them are true, there exists a solution for A3. First, I mean,
Wait a second.
I only count the first two. If there exists A1 and A2, and then it implies an A3 for the first two. Yeah, only count the first two.
Okay?
Yeah. So the remaining is the same method, but just we use the A3 and then the third number. And then the third number, for example, is 2. And then we make a dynamic array to store that A3 is larger than the last number. I mean the last number. I mean A4 and A4 smaller than A3. If both of them exist, so we can solve it.
Okay? I'm not, again, I don't see the algebra yet, but what I'm getting from your idea here is, you were going to tell me, suppose, let's say, I knew that I had something of the form A, B, okay? And is it that you're going to try to build up solutions for the 2-dimensional case? And the claim is that if you find a solution for the 2-dimensional case, the solutions for the 2-dimensional case can be combined, the claim would be.
Yeah.
Why is that? Let's think if that's true. So these are the examples of the 3 solutions for the 2-dimensional case, right?
I mean, it's CC, maybe CCD. There's 3 dimensionals can
Right.
relate to.
So there's 3, these are the 3
Yeah.
possible 2-dimensional solutions. Does everybody agree with that? If we have these solutions, is there necessarily a way to combine them? Is that what your idea is?
No, my idea is this one. If there is A, B, and C, D here, and A is equal to is larger than B, and D is larger than C, and then can prove it. But how to prove this? How to calculate this one? We can use the previous method.
Right. Okay. So the claim would be that okay, the question that I'm wondering about though is, when you do the previous method, you're now going to get a, yes, there is a solution of this type. But how do you know whether or not A is greater than B?
Just calculate the E and then compare with the third number.
The question is there only one way to do it for any particular pair?
But it's only, you need to know it's larger than or smaller than B.
Right.
So
I guess what you're saying is multiples of the same solution will keep that same property to it.
Yeah.
And that I believe, okay? So the claim here is that, right, if we have this, a situation like this, it's clear that one of these columns is redundant, and we're back to the two-dimensional case. Does everybody agree with that? So that does look like a good way to deal with it, okay? Any other ideas as to how you might do this one? Okay?
What's the complexity of this?
Well, what's the complexity of it? Okay, now one thing that they do is they give you a large number of things. They give you a total of, let's say, M triples. I think the first claim here, what's the complexity of your thing?
OM.
No, I don't think it's OM. I think it's O of M squared. Just right, you've got to try all possible pairs, okay, of the input here. As far as I can tell, you've got to try all possible pairs, okay? And for every possible pair, you will then get whether or not you have a solution of the type A, B, Oh, okay. Actually, wait. Is it the number of pairs times the square of the number of dimensions? Let's think what you're trying to do. Right? You've got to you're going to pick a pair of numbers: 1, 2, 5, 2, 3, 2, 1, 7. Because these two differ. You can solve the relative order of them differ. You can solve that, giving something that's either bigger or smaller than it, right? Now you have to do this for all subsets of columns though, right? Of which there are like 3 of them, right? So that looks to me that in the naive case you're going to be trying 3m squared possibilities, hoping to find the ones that you want. Is that right? Is there any way we can do it better than that? Or do we need to look at all m squared pairs?
I do it in another way.
How do you do it?
I made the 3-dimension into 2-dimension first. Suppose for a package S1, S2, S3, I make it to be the first element is S1 minus S2, and the second element is S1 minus S3.
Yeah.
And then we need to, maybe I write that.
Write it on the board, but quickly because we are running out of time.
Okay. If, here,
Yes.
suppose if there are S1, S2, S3, I want to make it equal. And then
Okay.
I use AI, BI, CI, and then I need to make
So you're creating 3 long equations. Is that right?
Yeah.
Okay.
And then I do the
An A equation, a B equation, and a C equation, right?
Yes. And this is A and B equation, and I do the subtraction, and it turns to be x plus x2.
What about B, C?
And the last is equal to 0. And then if I do the same thing to A and C, and I also can get A, C. Is equal to 0. And then I can regard this two as a new package x x1.
Have you said that the chemical number has the equation?
B1, this A2, this B2.
Right.
And then it turns to another
But you still have the
equation.
presentation
I regard this as a vector, 2-dimensional vector. And I don't have other place to.
Okay. Tell you what, let's maybe finish it up next class, just because we've got this. I think the class is over. But that's interesting. So your claim is that there's actually a way to do it that's faster, that avoids the m squared here.
Yes, I can do it in n log n.
Okay, so let's look at that next time. In the meantime, think about it, give it a try, and we'll talk about it next class. Okay? Thanks a lot. By the way, I've noticed more attendance on Wednesdays than on Mondays. And I have a theory it's because somehow we talk about the solutions on Wednesdays. Okay? But it's good to look at the material, the underlying material. So especially if you guys don't have the books, we should try to come on Mondays. So we talk about that as well. Okay, thanks for your attention. See you guys then.